Hello everyone. Today I'll discuss exercise 2.4, that is we will discuss about remainder theorem. Let us consider two numbers 15 and 6. You know that when we divide 15 by 6 we get the quotient 2 and the remainder 3. Do you remember how this fact is expressed? We write 15 as 15 over 6 into 2 plus 3. Observe that the remainder 3 is less than the divisor 6. Similarly, if we divide 12 by 6 we get 12 equal to 6 into 2 plus 0. What is the remainder here? Here the remainder is 0, and we say that 6 is a factor of 12, or 12 is a multiple of 6. Now the question is, can we divide one polynomial by another? To start with, let us try and do this when the divisor is a monomial. So let us divide the polynomial 2x cubed plus x squared plus x by the monomial x. Then we are getting, we divide this one, we are getting 2x cubed plus x squared plus x divided by x equal to 2x cubed by x plus x squared by x plus x by x, or 2x cubed squared plus x plus 1. In fact, you may have noticed that x is common to each term of 2x cubed plus x squared plus x. So we can write 2x cubed plus x squared plus x as x into x squared plus x plus 1. We say that x and 2x squared plus x plus 1 are factors of 2x cubed plus x squared plus x, and 2x cubed plus x square plus x is a multiple of x as well as a multiple of 2x square plus x plus 1. Consider another pair of polynomials 3x square plus x plus 1 and x. Here 3x square plus x plus 1 divided by x, we are getting 3x square divided by x plus x divided by x plus 1 divided by x. We see that we cannot divide 1 by x to get a polynomial term. So in this case we stop here and note that 1 is the remainder. Therefore, we have 3x square plus x is equal to x into 3x plus 1 plus 1. In this case, 3x plus 1 is the quotient and 1 is the remainder. Do you think that x is a factor of 3x square plus x plus 1? Since the remainder is not 0, it is not a factor. Now let us consider an example to see how we can divide a polynomial by any non-zero polynomial. Divide px by gx, where px equal to x plus 3x square minus 1 and gx equal to x plus 1. We carry out the process of division by means of following steps. And you see we have divided it here 3x square plus x minus 1. We are dividing by 3x plus x plus 1. 3x by 3x square plus 3x minus, it will cut and we get minus 2x plus minus 1. Right? And here you are getting, again if we put it here minus 2, then you get minus 2x minus 1, that is minus 2x minus 3x. 3x minus 2 is the quotient, right? Again here you see that we are getting x plus 1 minus 2, x plus 1 into minus 2, we are getting 2x minus 1. Step 4, we read the remainder minus 2x minus 1 as the new dividend. The divisor remains the same. We repeat step 2 to get the next term of the quotient, and we divide the first term minus 2x of the new dividend by the first term x of the divisor and obtain minus 2. Thus minus 2 is the second term in the quotient, that is 3x minus 2. Right? Then here you are getting, multiply the divisor by the second term of the quotient and subtract the product from the dividend. Right? That is, multiply x plus 1 and minus 2 and get the product 2x minus 2 from the dividend. This gives 1 as the remainder. This process continues till the remainder is 0, or the degree of the new dividend is less than the degree of the divisor. At this stage, this new dividend becomes the remainder and the sum of the quotient gives us the whole as a whole quotient. Step 6, here you see x plus 1, we are dividing it 3x minus 1, and last is remainder. Here you see that dividend is equal to divisor into quotient plus the remainder. In general, if px and gx are two polynomials such that the degree of px is greater than the degree of gx and gx is not equal to 0, then you can find polynomial qx and rx such that px is equal to gx into qx plus rx, where rx is equal to 0, or degree of rx is less than degree of gx. We say that px is divided by gx, and which gives qx as quotient and rx as remainder. In the example above, the divisor was a linear polynomial. In such a situation, let us see if there is any link between the remainder and the certain values of the dividend. In px 3x square plus x minus 1, if we replace x by minus 1, we have my p to the minus 1, 3 minus 1 whole square, minus 1, that is 1. So the remainder obtained on dividing px by 3x square plus x minus 1 by x plus 1 is the same as the value of the polynomial px at the 0 of the polynomial x plus 1, that is minus 1. Let us consider some more examples, that is 3x4 minus 4x cube minus 3x minus 4. If we divide by minus x by x minus 1, we are getting 3x cube minus x square minus x minus 4, and the remainder is minus 5. Here we have remainder minus 5. Now the 0 of x minus 1 is 1. So putting x equal to 1 in px, we see that p1 equal to minus 5, which is the remainder, right? That means find the remainder obtained on dividing px equal to s cube plus 1 by x plus 1. By dividing it, and the remainder is 0, right? Here we find px equal to x cube plus 1, and the root of x plus 1 is equal to 0 and x equal to minus 1. We see that p to the minus p minus 1 equal to minus 1 whole cube plus 1 or 0, which is the equal to the remainder obtained by actual division. It is not a simple way to find remainder obtained on dividing a polynomial by a linear polynomial. We shall now generalize this fact in the form of the theorem. We shall also show you why the theorem is true by giving a proof of the theorem. Let us find. The remainder theorem is let Px be any polynomial of degree greater than or equal to 1, or let A be any real number. If Px is divided by the linear polynomial x minus a, then the remainder is Pa. Here we will find the proof. Let Px be any polynomial with degree greater than or equal to 1. Suppose that when px is divided by x minus a, the quotient qx and the remainder rx, that is px equal to x minus a into qx plus rx. Since the degree of x minus a is 1 and the degree of rx is less than the degree of x minus a and the degree of rx equal to 0, this means that rx is a constant, say r. For every value of x, rx equal to r. Therefore, px equal to x minus a qx plus r. In particular, if x equal to a, in this equation gives us Pa is equal to a minus a q plus a plus r, that is Pa is equal to r, which proves the theorem. Let us see this result in another example. Find the remainder when this is divided by x minus 1. P is equal to this, and the 0 of x minus 1 is 1. If we find the P1, we are getting 2. So by the remainder theorem, 2 is the remainder when this is divided by x minus 1. Example 10. Check whether the polynomial qt 4t cube minus 4t square minus t minus 1 is a multiple of 2t plus 1. We're finding here that, as you know, qt will be multiple of 2t plus 1 only if 2t plus 1 divides qt, leaving remainder 0. Now taking 2t plus 1 equal to 0, we have t is equal to minus half. Also q minus half is equal to 4 minus 1 to whole cube plus 4 minus 1 to whole square minus 1 by 2 minus 1. Then we are getting the value 0. So the remainder obtained on dividing qt by 2t plus 1 is 0. So 2t plus 1 is a factor of the given polynomial qt, and that is qt is a multiple of 2t plus 1. Dear friends, if you like this video, please subscribe, like and share. Thank you everybody for watching this video.